Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the theorems on P groups and silo theorem. Let G be a group, finite group. Let H be a P subgroup of G. Then index of n of h over h is equal to index of g over h into mod. For proof, we know that n of h is equal to g belongs to g such that g inverse is equal to h. That is, n of h is a subgroup of G containing h. Let R denote the set of all right coset of h in G. Define f from R cross h to R by f of h x h is equal to h x h. Then R is a H set. As H is a P subgroup, coordinate of H is equal to P raised to n for some m. As P divides coordinate of H, we get coordinate of R is congruent to coordinate of RH into modulus P. But coordinate of R is equivalent to index of G over H. Hence, index of G over H is equal to coordinate of RH modulus P. Now, RH is equal to Hx belongs to R, so that f of Hx H is equal to Hx for all each h belongs to h. H is equal to hx belongs to R, so that hx h is equal to hx for each h belongs to h. H equal to hx belongs to R, so that x inverse hx belongs to h for each h belongs to h. Therefore, is equal to hx belongs to R minus x inverse hx is equal to h is equal to hx belongs to R, such that x belongs to n of h is equal to the set of all right coset of h in n of h. Hence, coordinate of RH is equal to index of nh over h. From 1 and 2 we get coordinate of g over h is equal to index of g over h is equal to index of n of h over h into modulus of p. Corollary, let H be a P subgroup of a group G. If P divides index of G over H, then n of H is not equal to H. We know that index of G over H is equal to index of n of H over H into modulus of P. As P divides index of G over H, we get P divides index of n of H over H. Hence, n of H over H is not equal to 1. Therefore, n of H divides H is not equal to 1. Therefore, H is not equal to n of H. We come towards silo theorem, silo force theorem. Let G be a group with coordinate of G is equal to P raised to N M, where P is a prime number and P does not divide M. Then first, G contains a subgroup of order P raised to I for each I, 1 less equal I less equal M. Second, every subgroup of order P raised to I is a normal subgroup of order P raised to I plus 1 for 1 less equal I less equal N minus 1. Proof. By Cauchy theorem, there exists a subgroup of order P in a G as P divides coordinate of G. Assume that there exists a subgroup of order P raised to I for each I less than N. Let H be a subgroup of order P raised to I. Therefore, cardinal index of G over H is equal to order of G divides order of H is equal to P raised to N into M divides P raised to I is equal to P raised to N minus I into M. As I less than N, we get P divides index of G over H. Therefore, index of G over H is equal to index of N of H over H into modulus P. As P divides index of G over H, we get P divides index of N of H over H. Therefore, P divides index of N of H divides index coordinate of H. Therefore, P divides order of N of H divides H. Hence, by Cauchy theorem, N of H divided H contains a subgroup of order P. Let it be K. Suppose that gamma from the function mapping gamma from N of H to N of H divide H be the canonical mapping, then gamma is an onto homomorphism. Therefore, gamma inverse of K is equal to x belongs to N of H, such that y of x belongs to K is the subgroup of N of H of order P raised to I plus 1. This shows that there exists a subgroup of order P raised to I plus 1 in G. By induction on N, the result follows. By the construction explained in H is subgroup of gamma inverse of K is a subgroup of N of H. Order of H is equal to P raised to I and order of gamma inverse of K is equal to P raised to I plus 1. As H is normal in N of H, we must get H is normal in gamma inverse of K. This shows that subgroup of order P raised to I is normal in a subgroup of order P raised to I plus 1. Next example, if order of G is equal to 2 raised to 4 multiply 3 multiply 7, then G contains subgroup H1, H2, H3 and H4 such that order of H1 is equal to 2, order of H2 is equal to 2 square, order of H3 is equal to 2 cube, order of H4 is equal to 2 raised to 5, and H1 normal in H2, H2 normal in H3, H3 normal in H4, and so on. There also exists a subgroup K of order 3 and a subgroup T of order 7 in G. Definition of silo P subgroup. A silo P subgroup of a group G is a maximal P subgroup of G. A silo P subgroup of a group G is a maximal P subgroup. In example, H4 is a silo 2 subgroup, K is a silo 3 subgroup, and T is a silo 7 subgroup. Remark, if coordinate of G is equal to P raised to M and P does not divide M, then the subgroup of order P raised to N will be silo P subgroup in G. If P is a silo P subgroup in G, then order of G inverse PG is equal to order of P, will imply that G inverse PG is also silo P subgroup of G for any G belongs to G. Any conjugate of a silo P subgroup of G is also a silo P subgroup of G. Second isomorphism theorem, second silo theorem. Now see here. Conjugate of a silo P subgroup is a silo P subgroup in a finite group, but any two silo P subgroup of G must be conjugate of each other. This will prove the following theorem.